Okay, so somebody can, you can move the camera, right? All right, so meanwhile,
when you say simple poles, do you mean just 1 over z minus z naught, or could it be,
yeah.
could it be a polynomial as well, or not?
Well, if it were if it's 1 over a polynomial, then if the roots are all different, then you have simple poles at different places. And then you could use this technique that I'm about to. In other words, you could just. All right, let me get to that point. So, suppose f of z just has at w. In other words, suppose the Laurent expansion around w is 1 over z minus. Is a minus 1 over z minus w plus the sum n equals 0 to infinity a sub n of w z minus w to the n. Well then, a sub minus 1 of w is just the limit z goes to w of z minus w times f of z. So you can compute the residue very easily in the case in which the residues are all, singularities are all isolated single poles. And if you had a polynomial, 1 over a polynomial, and the roots of the polynomial were all different, then you could use this trick on all the singularities. Okay, so that's easier usually than doing the integral. The integral is the other answer, which is 1 over 2 pi I. Integral around the point of f of z dz. On the other hand, as we saw in the case of that function, I think it was 1 over z plus 1, there it was pretty easy to calculate all of the residues at once. It turned out that only one was non-zero, and so that in fact would be easier than doing this sort of a subtraction. Okay. By the way, this calculus of residues has as a consequence, well, it comes from Cauchy's integral formula, and it has his integral theorem as a consequence, because if we take the function f of z equal to f of z over z minus w, and we integrate it around w, then we're going to get 2 pi I n minus 1 w for big F, and this is going to be 2 pi I, the limit as z goes to w of z minus w f of z over z minus w, and that's just 2 pi I f of w. So this is Cauchy's integral formula. Especially when we write this in the form f of z dz over z minus w. So f of w is 1 over 2 pi I times that. That's Cauchy's integral formula. So Cauchy's integral formula is a special case of the calculus of residues. All right, let's go to a more normal example then. Consider the function f of z equal to 1 over z minus 1 over z minus 2 squared. And so we've got a singularity here. This is the origin. We've got a pole at z equal to 1. We've got a double pole. I guess I'll write it like that. A double pole at z equal 2. And we're going to be thinking about doing an integral on a circle of radius 4. So it's going to look like this. And then the integral f of z dz by the residue theorem is 2 pi I times a minus 1 at 1 plus a minus 1 at 2. And the a minus 1 at 1 is easy to evaluate. It's a minus 1 at 1. We'll just use this trick here, and that is the limit z goes to 1, z minus 1 on f of z, which is to say the limit z goes to 1 of, well, the z minus 1 cancels, we get 1 over z minus 2 squared. Well, that's just 1 over 1 minus 2 squared, which is just 1. But if you do the explicit integral, you also get the same number. In other words, that's the same thing as the integral of dz over 2 pi I z minus 1 z minus 2 squared. That's also. But now a minus 1 at 2 is now see, a minus 1 at 2 would be tricky to do. You can't use this trick for that. So instead we have to do the integral dz over z minus 2 squared z minus 1. Well, by Cauchy's integral formula, this is d by dz of 1 over z minus 1 evaluated at the point z equals 2. This is, I mean, when you, every time I see formulas like that, I think, God, this is amazing. Oh, by the way, somebody asked me, unfortunately he's not here, whether Cauchy was opposed to the French Revolution. No, because he was born the same month as the French Revolution. He was born in 1789, back in August. And a few years later, there was the Reign of Terror in 1893, 1894. His family then moved to, I think it was Arcueil, where curiously we ran into two other French mathematicians, one of whom, I can't remember either of them, but anyway, this one happens. So no, he didn't have a big role in the French Revolution. He did later, however, work for Napoleon. He was designing, I think, harbors that Napoleon was going to use to launch ships to invade England. All right, anyway, so we've got this derivative here, and this is not very hard to evaluate. We get minus 1 over 2, whoops, it's 2. 2 minus 1 squared, which is minus 1. So what we get then is that the whole integral of f of z dz around this contour radius 4 is 0. It's the sum of the two residues. One is minus 1, the other one's 1, and so we get 0. However, we could have seen that it was 0 directly, because this function at large z goes down as 1 over z cubed. Okay? So if we consider, and all the singularities are within the circle of radius 4, so we can expand the contour out to infinity, so that instead of here, it's just this huge contour of radius r. Then the perimeter, which is dz, will go as r, but the function goes as 1 over r cubed. So the absolute value of the integral of f of z dz around this big circle radius r is bounded by some number m times r squared, and that goes to 0 as r goes to infinity. So in other words, we could have computed this integral not using the calculus of residue, simply by changing the contour, not shrinking. In other words, the calculus of residues, we computed the contour by shrinking it down to these two mini contours, these infinitesimal contours. Instead, we'd blown it out to infinity. We would have seen immediately that it had to be 0. Are there any questions? Remember, I have chocolate. And, please do ask questions. I'm not in the business of ranking graduate students according to competence or education or anything. I issue grades only because the department insists on it. But, so I wish you guys would ask questions.
Why is it obvious? Because of the amplitude height?
Why is what?
It's obvious that it's 0 when you get.
Yeah. And the reason is that f of z goes down as suppose z, on this contour, z is equal to r dpi theta, where r is u, light years. And f of z goes down to 1 over r cubed. And the perimeter is only 2 pi r. So the whole thing goes down as 2 pi over r squared. In fact, that's what we say here. It's actually 2 pi over r squared. That is a very intelligent remark. Yes. Brilliant. We have here Aaron's theorem. Integral dz over any polynomial of root n, as long as n, the order, is greater than or equal to, I would say 2. It doesn't even have to be 3, as in this case. But just greater than or equal to 2, then this will have a bunch of isolated singularities. And the integral, as long as you're outside all of the singularities, you then shoot it out to infinity and you get 0. So that's 0. Okay? Now this business of having a contour, all of which or some of which is out at infinity, and therefore that contour or that part of the contour is 0, that's what I call a ghost contour. In other words, the value of the integral along the contour is 0. So we can add or subtract a ghost contour anytime we want. These ghost contours normally are not closed. This is a closed ghost contour. But sometimes they're not closed. Sometimes they're just segments of the closed contour. All right, so as an example, let's look at the Fourier transform of Gaussian. And in fact, this is something that I promised you guys we would prove when we were doing Fourier transforms way back when. I said that I showed you how to do the Fourier transform of Gaussian, and then I said, well, there's this little technicality here that we'll prove when we do complex variable theory. So let's consider, what I want to show then is that the integral of a Gaussian along two parallel paths in the complex plane is the same. And so what we're going to do is do the integral e to the minus m squared z squared, where m is real, dz, and we're going to go, this contour is going to go from minus r to r to r plus, what do they call it? Ik over 2m squared. No, it doesn't matter, it's any real number. But let us say ik over 2m squared. And so the contour goes like this, and then it goes like this, and then it goes down there at minus r plus okay? All right, so what we want to do is we want to first show that this contour integral is 0. Well, it's obviously 0 because this is an entire function. There are no singularities, and consequently, this thing is 0. Now, actually, what is it? Well, it's an integral from minus r to r, e to the minus m squared z squared dz, plus the integral from r to r plus I k over 2m squared e to the minus m squared z squared dz, plus the integral from r plus ik over 2m squared. I don't know why I didn't replace this by just some imaginary number, not carry this stupid. Plus ik over 2m squared. Did somebody ask a question? Yes. It's from minus r to r, from r to r plus, from r plus to minus r plus, and then finally the integral from minus r plus ik over 2m squared to minus r of e to the minus m squared z squared dz. Oh, it's just because that was what occurred when we were doing the Fourier transform of Gaussian back in chapter 3. Okay, so I'm going to change my notes here and just make that some complex number, some imaginary number rather than this crazy, complicated combination. Okay, any questions? I have a question. How was the pizza? Good? All right. Okay, these integrals from r to r plus ik and from minus r plus ik something to minus r, those are both 0. The reason they're 0 is that the real part of z is equal to r, so this is e to the minus m squared r squared, apart from a couple of factors that aren't important. All right, so this is essentially e to the minus m squared r squared on this interval, and the interval is finite. It's just from 0 to k over 2m squared. Similarly, here, this is essentially e to the minus m squared r squared. So these two things are ghost contours. These things over here, these are ghost contours. I have this course really synchronized. It would have been on Halloween that I did ghost geometry.
I thought the ghost contours were infinitely far away.
Well, they are. We're taking the limit r goes to infinity because we're trying to do the integral from minus infinity plus infinity we got solved. Okay. And so what this tells you then is that that since the sum of these is 0, and since the one from r plus I something to minus r plus I something is minus the integral from minus r plus I something to plus r plus I something, what we get is that the integral from minus r to r of e to the minus m squared z squared dz is equal to the integral from minus r plus I, let me just call this C, to plus R plus IC of E minus M squared C squared EZ. Which is to say, just so I write it really explicitly, it's equal to the integral minus R of E to the minus M squared Z plus IC squared EZ. Or to now write everything in terms of explicitly real and imaginary variables, the integral minus infinity plus infinity e to the minus m squared x squared in x is the integral from minus r to r e to the minus m squared x plus ic squared dx. And that's what we actually wanted in chapter 3.
You mean minus infinity on the second hand?
Yes, thank you. All right, I'm going to do this. All right, now, the next topic is one that's relevant, particularly relevant to any of you who are going to go into optics or biophysics. So let me show you why. The subject is third harmonic. Third harmonic microscopy. And what are we dealing with? An ultra-short laser pulse, intensely focused in a featureless medium, generates a third harmonic electric field in a forward direction proportional to the integral in this particular integral. The integral is called T3 and is proportional to chi3, which is a number, the cube of the electric field, an integral from minus infinity to plus infinity e to the I delta k times z dz over 1 plus 2iz over b squared. And in fact, I'm not sure why I use z. I could have used x here. In other words, this z is real in this integral, so it's effectively an integral dx. What is b? b is equal to 2 pi w, that's a w, not an omega, w0 squared, the index of refraction over the wavelength of the light, which is also k w0 squared. So n of omega is the index of refraction, and w is the transverse waist of the Gaussian beam. So the Gaussian beam is focused like that, and this distance here is w. In other words, it's, I don't know, half width and half maximum. It's called the waist radius of the Gaussian beam. And it's defined actually as E of R is E to the minus R squared over W0 squared. Okay, so that's the definition of W0. Now, normal dispersion is when you have dn of omega, d omega greater than 0. If we have normal dispersion, dispersion causes having dn d omega non-zero. Normal is when it's positive. Then the shift in the wave vector, dk, turns out to be 3 omega times n of omega minus n of 3 omega. This is what dk is by definition, over c, and this is less than 0. And the reason for that is that if dn d omega is positive, then n is bigger at 3 omega than it is at omega. And so this part is a definition. Or, well, it's part of a more elaborate treatment that I'm not going to go through. So since dk is negative, this exponent here is going to have a real part that's negative if z is in the lower half plane. Because if z has an I in it, then we have I squared is minus 1. That makes dk positive because dk is negative. So then you want the imaginary part of z negative. We have 3 negatives. And then we get some big damping. So what we're doing is
Isn't z real in this case?
well, I started out with z real, then I promoted. We start out really with an integration over x that's real. And I promote x to a complex variable z, and then I'm adding a ghost contour. So the original integral does this, from minus infinity to plus infinity. Then I add a ghost contour, or let us say from minus r to r. I then add a ghost contour where z is equal to r e di theta, where theta in the interval pi less than theta less than 2 pi. Okay, so that's the ghost contour. Because on this contour it's 0, and you can say, well, what about over here? Because you're not very far. You're not already way down in negative y. But over here, you're already damped because, well, let's see, it didn't, yes, you got a 1 over z squared here. Okay, you got a 1 over z squared. And so that's enough to give you, to allow you to cancel this part. Ignore that, and once you're down to the bottom part, you've got heavy damping because it goes down exponentially. All right, so altogether it's a ghost contour. And the limit r going to infinity. Okay. All right, so the upshot then is that this integral is the same thing as the integral around this total contour, which is now a closed contour along the real axis down underneath, down lower half plane. And then what do we find? Well, are there any singularities here? No, the only singularity is in the upper half plane. Because when z has a positive imaginary part, then you get this thing to cancel. All right. So that means, in fact, the singularity will probably say where it is. Well, I don't see it, so let me just compute it. It's z equal to minus b over 2i, minus b over 2i, which is to say IB over 2. And B is something that's positive. So there's a singularity over here, and in fact it's a double pole at that point. So this whole integral then is equal to what? Yes, 0. It's an integral of 0 because it's an integral of an analytic function on a contour that doesn't enclose any singularities. Okay, so what does that mean? That means that the signal that you get, E3, forward direction, 0. But this, and so you might say, well, this is a lousy form of microscopy, the signal is 0. But that's because I worked it out for the case in which the index of refraction was constant in space. What you actually do is you have the beam like that. Then if there's no feature here, you get no signal. But if there's an edge of something so that the index of refraction changes from here to there, then you no longer have up here the constant, spatially constant index of refraction, and instead, as you go along with this integral, something happens there, and so then you get a signal. So with this third harmonic generation, what you see are only edges, or effectively features. You see changes in the index of refraction. You don't see the featureless part. So if you're looking, for example, at a cell, and you're outside the cell, no signal. If you move the thing so that the waist of the beam is at the edge of the cell, where the phospholipid bilayer is, then you have a big change in the index of refraction, because the phospholipid bilayer, you see, these are polar head grooves. These are polar or negatively charged head grooves, and of course the resilience of them. And so if this is water, in fact, the dielectric constant here is something like 80, the relative dielectric constant is 80. In here it's 2. Over here, it might be 4 because we're in the head groups. And down here it's 80 again. So you have all these changes in the dielectric constant, and that affects the index of refraction. So that's what you. In fact, does anybody remember the relationship between the index of refraction and the dielectric constant? Anyway, I'll try to look it up and put it in the notes. Okay, so that's how third harmonic microscopy works, and the interesting thing then is that the advantage is that it lets us see features rather than just the uniform background, which of course has no information. But it doesn't need to be a cell. You could be talking about some material sample. It's just when there are changes, you see the features of it. All right, next example. We want to compute this integral, I of x. There's an integral minus infinity plus infinity to k. EBI kx over k squared plus m squared. Okay, so what is this? This is the unnormalized, or this is, let's say, this is the Fourier transform without the 2 pi's of the function 1 over k squared plus m squared. Let's take the case x greater than 0. Then, for x greater than 0, if k has a positive imaginary part, this thing is exponentially damped. Moreover, we also have a 1 over k squared here, so we get damping from that also. So that means that we can add a ghost contour in the upper half plane like that. Okay, so then what? Then that means that what we're doing here is the same as the integral over this total closed contour of EBI kx over, and let me factor this, k minus im, k plus im, dk. That's our integral. Now we just use the residue theorem, and it's going to be, in fact, when I did the residue theorem, in the notes, I actually did the two integrals. Well, the one integral. But here we see this is actually simpler, isn't it? This is going to be, all right, so let me do it the new way. Invented the time of the poet, you understand. I want to use the right notation though. A minus, well, this is going to be 2 pi I. A minus 1 at Im plus A minus 1 at minus Im. And this will be 2 pi I. A minus 1 at Im, well, it is you take the limit. Let me leave out the limit. All right, let me put in limit. I'll put in make this clear. The other way of doing it is in the notes, so you can read that one as well. Z goes to Im in the first case, Z minus Im times this whole thing, e to the I kx over, well, it's k, not z. K is the complex variable. K minus Im, K plus Im, plus the limit K goes to minus Im, K plus Im over K minus Im, K plus Im, e to the I kx. All right? These guys cancel. Let K go to Im, that's 1 over 2 Im, so this is 2 pi I. E to the K is equal to Im, and so this gives us minus kx, right?
10 seconds.
Times, where's the m? Oh, yeah, I'm sorry, you're absolutely right. In fact, wait a second, I went too fast here. If we're doing this integral, then we just have this singularity, not both of them. Because this other one down here, we don't pick up. So we just get this. Okay? We just have this. And these cancel. And so we have 2 pi I e to the I kx. Okay. K is equal to Im. So this is minus mx over K is equal to 2 Im. And that is then pi over m e to minus mx. Which, in fact, is what I got by actually doing the contour integral. Okay. And in fact, for the second one, let's consider, in the second case, let's consider the case where x is negative. If x is negative, then we have to add the ghost contour in the lower half plane. And if we do the ghost contour in the lower half plane, well, this time let me just do the contour. Then we get I of x is integral, now it's integral in the lower half plane, an integral that goes around the lower half plane over k minus Im, k plus Im, and now this is Well, this is the part that's singular now, because we can say we first turn it into an integral around this whole contour, and then we shrink it to this. And when we shrink it to that, the singular part is k plus im. The rest of it we can just pull out as e to the ix times k, and k is equal to minus im. And then we have minus 2im here. And then we have the integral dk over k plus im. And that is just 2 pi I, well, it's just 2 pi I, isn't it? So we get oh, I'm sorry, this is the one that I had to pull out. All right, wait a second, I'm getting confused now. This is the one that's singular. We pull that one out. We have k plus im. Oh, the integration is clockwise rather than counterclockwise, so that gives us a minus sign. So altogether we then have e to the xm over well, let me just copy it. It's 2 pi over 2m. And altogether then it's pi e to the nx over m. But this isn't the case x less than 0. Case x positive is this. So the general case is that I of x is pi over m e to the minus m absent value of x. So that's the full integral. Now, some of you have frowns, and so do ask your question, and I'll go over in more detail the part that I went over too quickly. Say it again. Where? Here?
Yeah.
Okay. Here, what we do is you see we're shrinking the integral down to the integral around the point minus im. That's the singularity. And so when we're doing this integral around there, we can just replace k by minus im in the non-singular part. So I pull out ix times minus im, and then here we have k minus im, so that's minus 2im. I just remembered what it is that my voice reminded me of during this whole intro. It's one of those Dr. Seuss children's stories where he has this, he says, I am about 100 times. I never liked this story. I hope the kids like it. I'm certainly different enough. All right, anything else? I owe you a time. Hold on. You don't want anything? All right, so that's that. Another example. Let's consider the integral j of x. Now we've got an integral minus infinity plus infinity e to the I k. This is again a Fourier transform. K squared plus m squared squared dk. By the way, you see now why people know what the Fourier transforms are of so many functions. The reason is that you have this e to the I kx here, and you can add a ghost contour and do the integral quickly by complex variable methods. All right, so let's see how we do this one. Well, first of all, let's factor. So factor the denominator. We get e to the I kx over k plus im squared k minus im squared dk. Now, if x is, for some reason I did, okay, x is positive. For x greater than 0, if x is greater than 0, then we're going to have damping in the upper half plane. Because we have 4 powers of k in the denominator, we can add a ghost contour, so we're doing this as our contour. Now the singularity is due to this.
When can't you add a ghost contour?
When it's non-zero. When the contour, when the integral of the function along that segment of the contour, along that contour is non-zero, then you can't add it because it's not zero. You can only add 0 to something that you're trying to compute. Great question. You want another piece? All right. So now by Cauchy's integral formula, this is just equal to 2 pi I d by dk, and that's because we have a second power here, of everything else, which is this. E d I kx over k plus im squared. Of course, evaluated at k equals im, which is this pole here, so there's a double pole there. And that, in fact, is equal to pi over 2m squared, x plus 1 over m, even minus mx. Now, if on the other hand x is negative, then we do this. But now when we encircle this pole down here, which is a double pole, we're going around the wrong way, so we get an overall minus sign. And the answer is minus 2 pi I d by dk e to the I kx. And now it's this term, k minus im squared. And that turns out to be pi over 2m squared minus x plus 1 over m e to the mx. This is for x less than 0. So altogether we get this is equal to pi over 2m squared after value x plus 1 over m e to the minus m after value x. Okay. So that's the actual result. All right, do you have any questions? I think one of the things that may be inhibiting you is that I sometimes, in the tone of my voice, I sort of give the impression in the tone of my voice that the argument is clear and inclusive and there can't be any reason for doubt or any questions, and so maybe I should talk more like younger people do, with a question mark at the end of every sentence. Okay, I'm going to turn the thing. But you should keep turning it. I'm going to forget. Okay, now we have a complex Gaussian integral. I is the integral minus infinity to plus infinity e to the wx squared dx. So w is complex. It's equal to u plus iv. I'm going to write it as rho e to the iv, because rho is greater than or equal to 0. In fact, we're considering only the case rho greater than 0.
What do you mean because rho is greater than?
Excuse me?
You're saying it is greater,
Rho is greater than 0.
which is.
If rho were equal to 0, W would be 0 and the integral would diverge. And the integral also will diverge unless the real part of W is negative. And so U less than 0 is the same thing as pi over 2 less than phi less than 3 pi over 2. So in other words, we're saying here that this number W is somewhere in the left half plane, not counting the y-axis. All right, well, the first thing to do, at least doing it the way I want to do it, and there are probably many ways of doing this integral, I'm going to write it as 2 the integral 0 to infinity e to the w x squared dx. Now I'm going to promote x to a complex variable z equal to r e to the I theta. And then what we're going to have is 2 integral 0 to infinity e to the w z squared dz. And for the moment, z is still real. We can't, I mean, even though we're saying that we're going to make z a complex variable, we can't shift the contour yet till we analyze what's going on. Okay. When is the real part of wz negative? Well, the real part of wz, in fact, wz squared, I mean, is less than 0 if phi plus 2 theta is equal to pi, or equivalently, theta is equal to a half times pi minus phi. And remember, phi is somewhere near pi plus or minus pi over 2. So we want, when we deform this contour from 0 to infinity, we want to keep it within the range of, in the part of the complex plane in which we get the real part of wz negative. Well, the real part of wz will be negative as long as phi plus 2 theta is less than 3 pi over 2 and greater than pi over 2. Which is to say, as long as theta is less than 3 pi over 4, let me get rid of some of that writing. 3 pi over 4 minus pi over 2 and greater than pi over 4 minus pi over 2. So we need theta in that region. But we also know that phi is between pi over 2 and between pi over 2 and 3 pi over 2. And so consequently, the integral, if we let z equal to r e to the I theta, well, which is, I don't know why I use theta prime. All right, so let me fix this. The real part of z will be negative as long as theta satisfies this, and in particular, it will be true if theta is greater than or equal to 0 and less than or equal to pi minus phi over 2. So, in other words, this interval lies inside that interval. And the reason for that is that phi lies there. So, if we do that integral then, in other words, if we add a contour like this, it'll be a ghost contour as long as we keep theta in this region here. And what is this angle here? This angle here is, in fact, pi over 2 minus phi, or pi minus phi over 2. And, of course, phi can be almost as big as pi, or can be bigger than pi. If phi is less than pi, then this is positive. If, in fact, phi is over here, if phi is bigger than pi, then this is in fact negative, and what I should say, okay, so this is for the case phi less than pi. For the case phi greater than pi, what we want is pi minus phi over 2 less than or equal to theta less than or equal to 0. So it depends on where phi is. But in either case, so in other words, if phi is less than pi, this is the contour. If phi is greater than pi, then it looks like this. Okay? And what about this function? Well, this is an entire function. So the integral around the pi, around the edge of the pizza slice. The integral around the edge of the pizza slice is 0. Also, the integral along here, that's a ghost contour because the real part of wz squared is negative, and we're shoving the thing out to infinity. Right. So the real part of that is negative, and this thing is proportional to r squared. Okay, so that's strictly negative. So that means then that the total integral, that the integral along here is equal to the integral along there, or equivalent to the integral along here is equal to the integral along there. But on this integral, that thing is negative. And on this integral, wz squared is negative. And so, what we get, the thing we want, I, is equal to twice, or rather, this integral is I over 2. And so the rule we have is I over 2 plus this integral e to the wz squared dz along this pizza slice, the edge of the pizza, which is either like that or like that, depending on where phi is equal to 0. And so that means that I is minus twice the integral either this way or that way, e to the wz squared dz. On the other hand, this thing is real and negative here. So this thing is equal to minus 2 integral from infinity to 0 e to the minus rho, what did I call it? Let me go more slowly here. It's e to the, all right, let me follow the notes directly so that we don't get any screw up here. So what we get is I is equal to 2, and now we're having integral wait a minute. Okay, so I is equal to 2, integral 0 to r e to the I theta, e to the wz squared. All right, this is, I have to write this. 0 to r e to the I theta, e to the wz squared dz. And now this is 2 e to the I theta integral, that's e to the minus rho r squared dr 0 to r. The e to the I theta comes from the dz, and here what we have is dz is equal to e to the I theta dr. Normally when we did a dz, we were going along theta. Here we're going along r, so there's no extra I. And the limit, when you take the limit as r goes to infinity, you just get 2 e to the I theta integral 0 to infinity e to the minus rho r squared dr, and that's just a well-known integral, so we get e to the I theta square root of pi over rho. So putting everything back together, our original integral is equal to I square root of pi over w, or the square root of pi over minus w. Where did the I and so forth come from? Well, theta, where we chose theta and phi to be this, so the thing would be negative on that edge of the pizza slice. And so that means then that theta, in fact, is equal to pi over 2 minus phi. So e to the I theta is e to the I pi over 2 minus phi. E to the I pi over 2 is I, and then e to the minus I phi e to the minus I phi, then the e to the minus I phi goes down, combines with the w, and what I'm puzzled with is why there is a hold on, it's over here. Theta is pi over 2 minus phi over 2. And so we have here, this is equal to pi e to the minus I phi over 2 square root of pi over rho. That's e to the minus I phi over 2. That means it's the same thing as I times the square root of pi over rho e to the I phi, which is w. So that's 1 over square root. That's I root pi over w. And then you can pull in the I by making that a minus w. All right, well, that's enough. We'll do logarithms and cuts next Monday. And I'm then going to,